In this lesson, we create a control chart for individual measurements, calculate the control limits for a sample size of 5, and compare them with process capability requirements. And hello again to this lesson, which essentially has 3 learning objectives. After this lesson, you should understand why the control limits for an X chart for a sample size of greater than 1 are different from those for a sample size of exactly 1. You should also be able to use tables to calculate the warning and control limits for any sample size. And you should know the warning and control limits differ from the specification limits when a certain process capability is specified. This lesson is divided into 3 chapters. In the first chapter, the characteristics of the X charts for a sample size of 1 and greater than 1 are explained and the differences are worked out. In the second chapter, we use an example to calculate the 95% warning limits and the 99% control limits. In the last chapter, we then compare the control limits with the specification limits when specific process capabilities are specified. To be able to classify the X chart in comparison to the other quality charts, this picture shows the connection between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics shown on the left can be divided into 2 different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. Second, there are the attributive characteristics. Those are all characteristics one can only count, but we don't want to go into detail about them here. On the right, we have the different control charts for variable characteristics with a white background. These are also called Shewhart charts, named after American Walter Andrew Shewhart. As you can see, there are 3 control charts for monitoring the process location and 2 control charts for monitoring the variance, which means the spread. The X chart is one of the location charts. Let's start with the elements of an X chart for a sample size greater than 1 and the differences for a sample size of just 1. As an example, we use the diameter of this piston again, which has a nominal diameter of 60.1 mm. The tolerance is irrelevant for the calculation of the warning and control limits. This only becomes important again when the process capability is also to be calculated. An excerpt of an X chart for a sample size of 1 is shown on the left. On the right side for a sample size of 5. Comparing the upper and lower control limits with each other, it can be clearly seen that the control limits are further apart with a larger sample size when all other parameters remain the same. We will go to the bottom of the reason for this next. A non-interference probability of 99% was set for both control charts. Based on this probability, the control limits were calculated and drawn into the charts. For the left side, this means that the probability is 99% that exactly this one value of the sample is within the limits. For the right-hand side, this means that the probability is 99% that exactly 5 values. This means all values of the sample should be within the limits. From this follows that the probability that one of the 5 values is within the limits cannot also be 99% if this is to apply to all 5 values at the same time. So, P total is the probability that all 5 values of the sample are within the limits. Expressed in relative probability, that's 0.99. From the multiplication theorem of probabilities, it follows that the probability that exactly one of the 5 values is inside the limits is 0.99799. So 99.799%. Due to this higher individual probability, the limits must be set further apart. And since the individual probability that a value will be outside the limits increases as the sample size increases, the limits must also get wider apart as the sample size increases. It may be hard to grasp in this short space of time, but this lesson isn't intended to provide the exact mathematical proof, just a more general understanding of why a larger sample size needs wider control limits. The more precise mathematical derivation is explained in a separate lesson. A value outside the limits always signals a process that may no longer be under control and should be readjusted. A quality control chart for a sample size of 1 looks essentially the same as one for the sample size of 5, 10, 15 or any other value. Only the control limits are adjusted to the sample size, and the control chart must have more space to be able to write down all values. The formulas for calculating the limits are summarized on the left-hand side. In this lesson, we will only use the right side with the factors EC and EW. How to calculate these factors yourself is explained in a separate lesson. For this, you need the formulas on the left side. In these formulas, mu is the arithmetic mean of the population. Mu with this head or roof on top is the mean of the sample. And by the way, this head sign is called circumflex. Sigma is the population standard deviation, and sigma circumflex or head is the sample standard deviation. EC is the factor for calculating the limits for a 99% non-interference probability in the process. EW is the factor for calculating the warning limits. The U term describes the quantile of the standard normal distribution and, as already mentioned, is covered in a separate lesson. As a quick reminder, the values for the mean mu and the standard deviation must be determined beforehand. For our example, this means that, for example, 50 pistons from a series production were previously removed and their diameter measured. Mu and sigma were then calculated based on this data. If there is no series production from which this data can be accessed, the data must be determined as part of a pre-series. For our further calculations, we assume that this has already happened. A mean value of 60.11 mm and a standard deviation of 0.03 mm were calculated. Both values can be found in the header of the control chart. After the values for the mean and the standard deviations are available, only values for the factors EC and EW are missing. Values for these factors can be found for different sample sizes in corresponding tables. Values for EW and EC for a sample size from 1 to 5 are listed here as examples. For a sample size of 5, we take from the table a value of 2.569 for EW and a value of 3.089 for EC. Both values were also entered in the header of the control chart. If you now insert these values into the formula for the upper control limit, a value of 60.2 mm is calculated. This control limit has also been drawn on the control chart. A value of 60.19 mm results for the upper warning limit, and a value of 60.03 mm is calculated for the lower warning limit. The lower control limit is 60.02 mm. With a probability of 95%, all values will be between the warning limits of 60.19 and 60.03 mm. And with a probability of 99%, all values will be between the control limits of 60.2 and 60.02 mm. Only when one of the limits is exceeded, it is a signal that the process is out of control. If one value is outside the control limits, the process must be readjusted. Here again, the control limits for different sample sizes in comparison. If the parameters are otherwise the same, such as the spread, then it can be said that the larger the sample size, the further apart are the limits. A somewhat more precise proof for this was already given at the beginning of this lesson. And if you want to know exactly, I recommend the separate lesson on this again. Finally, let's compare the control limits with the specification limits again if the process is to meet some given process capabilities. Just a quick reminder. We are still looking at the diameter of the piston shown here, which is said to have a nominal diameter of 60.1 mm. We will see in a moment how the tolerance and the minimum and maximum dimensions were calculated. In this case, instead of deriving the tolerance from technical considerations, the tolerance should be selected in such a way that a specific process capability is met. The critical process capability formulas are shown on the left. Underneath, these were transposed to the upper and lower specification limits. The specified critical process capabilities should be 1.33 and 1.67. For a process capability of 1.67, using the already known values for the mean value of 60.11 and the standard deviation of 0.03, this results in an upper specification limit of 60.26 and a lower one of 59.96 mm. Both specification limits were plotted on the control chart. With a process capability of 1.67, at least 99.999% of all values will probably be within the specification limits. If you calculate the specification limits for a process capability of just 1.33 in the same way, you get a value of 60.23 and 59.99 mm for the upper and lower specification limits respectively. These were also entered in the control chart. If the requirement for the process capability is a value of 1.33, then at least 99.99% of all values will probably be between these specification limits. In conclusion, it can be summarized that the greater the required process capability, the further apart the specification limits are if the spread remains the same. The warning limits have a safety margin to the control limits, and the control limits have a safety margin to the specification limits. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The larger the sample size, the further apart the warning and control limits are, since the probability that a value is outside the limits increases. The factors EW and EC for the standard deviation differ depending on the sample size. A value outside the control limits indicates an out-of-control process. If you found this lesson helpful, please let me know and leave a comment. Thank you for that. Take care and see you next time. Bye.